Okay, so first two talks I gave were more or less tutorial. I was asked to do something rather research-oriented. So this is a research project which I supervised, actually. Alexander was my honor student last year. And so basically I'll report on the results he came up with, which are incomplete. So this is actually a fairly preliminary study. But before I get into that, I want to argue with Nozer. Of course, in this case, it's a little bit like Clint Eastwood arguing with Obama, the empty chair. He's not here to respond, but all the better. All the better for me. I'm safe from counter-argument. Sorry?
Somebody could pretend to be Nozer.
Okay, if somebody wants to pretend to be Nozer, that's fine with me. Okay, so his principle, I encountered it over breakfast today, that people were accepting this, and I find it fairly remarkable. So basically, I'll just express why I find it remarkable and leave things up to you. I won't really argue about it that much, but I'll give some reasons. So he said in general, posterior probabilities or conditional probabilities of this type ought to be identical across subjects. So that's the P and the P prime. They're meant to be representing the subjective states of two rational Bayesians. Okay, he thinks that, and other people think that that's a plausible principle to apply. In general, it's supposed to mean not universal, but pretty widespread. So you acquire information in your life, or you run experiments and acquire data out of the experiments, and you condition on that, and you should end up in the same place. Now, I think a far more plausible principle than that a priori is this likelihood principle, that likelihoods ought to be the same. If you look at most of the hypotheses people are investigating in science, they're causal hypotheses. They explain how the data are generated. And so if you have the same hypothesis generating data in the same way, and you have two rational scientists evaluating that, they should come up with the same probabilities. So given both principles, then, we can certainly just apply Bayes' theorem. We can swap in P prime for P here because of the likelihood principle. We can do the same thing on the denominator for the same reason, because that's just an average mixture of likelihoods. And so we're going to get this identity. Okay. But then what does that mean? That means that since these are meant to be identical, I'll just move on to the next. Okay, if it's also the case, according to Nozer's principle, that the conditionals there are the same, then it just follows immediately by substitution that the priors are the same. So the implication of this principle, then, is that everybody's probabilities are always and everywhere the same. Well, to within whatever in general means.
So what James does is put the background information X explicitly together with E. So everybody has a different background information.
Okay, so you can get some variation that way. Fine.
I wasn't aware that Nozer adhered to that first principle.
That's what he asserted.
Okay. That's good.
Okay, so if you treat background information the same as evidence, my argument still holds, but you might then argue that, okay, everybody has this very background information that somehow accounts for their different priors. But I prefer a different view anyway. Basically, what we have is a continuum. James and some other objectivists say you should have a unique distribution. It should be specified in effect by the language you adopt in which you frame problems, and then you do entropy. There are other objective people like Carnap who again invoke a certain kind of linguistic structure and then apply a uniform distribution over that and say, okay, well, this is what rationality is. You adopt this prior. So in any event, there are a group of people saying that there's a unique prior. Everyone's obliged, if they're going to be rational, to have exactly that and only that. Okay, you can vary it with background information, but it's still a unique prior. And then there are people like Dave Finetti who says anything goes. Anything that satisfies the probability axioms is good enough for him. If that means that you can never learn anything because you're assigning zeros and ones to all kinds of synthetic propositions, so be it. It's still rational. But basically, my position is that everything but these two extremes is more rational than the two extremes anyway. So here's my suggested principle, that in the limit of the evidence we converge. So there's no requirement that we start at the same place. That does rule out quite a variety of extreme probability distributions that won't converge, an infinite variety, of course, but then there's an infinite variety of other distributions which will converge on certain kinds of evidence, some exchangeability in some cases, or whatever you want to know.
So basically, when the evidence overwhelms whatever background information or preconceptions you have, then you converge.
Yeah. Okay, so that's my alternative. Now, to discretization. So first of all, just as motivation, why discretize? If you're doing regression, you don't need to, you don't want to. You want continuous properties and so on. But if you're using classification trees, naive Bayes models, Bayesian networks in general, for prediction and modeling, then you're going to want to discretize because the algorithm's more or less required. So the question addressed here is how best to discretize. So the simplest possible approach is to just slice things up into equal width bins. And for some simple problems that will work. But in general, as problems get less simple, it falls off right away. Equal frequency binning. So EFB3 is just slicing things up into quartiles. So you just count until you have 25%, and there's your first demarcation. That's nearly as simple as equal width binning. It works across a broader range of cases. And performance can be reasonable if you can select the right model class, that is to say, the right number of cut points to discretize with. Since prediction is one of the prime uses for all of these models, an obvious choice is to do some sort of optimization search for discretization that optimizes predictive accuracy. That's this maximum likelihood approach, and I'll throw that's in the mix of things that we looked at. That leaves open complexity control. So here comes in what is actually, in the machine learning world, at any rate, the most popular discretization technique today. That's due to FIAD, entropy MDL, it's a version of MDL. So it minimizes the class entropy in the target variable, and it trades that off in a natural way against simplicity of discretization, which is basically just the number of cut points. So in other words, it searches for a minimum value for this sort of information theoretic thing. So you have the complexity of the model penalized according to an MDL protocol, and then entropy accounting for what's left in the variation of the data. So trying to minimize that. So like I said, this is popular, and it's the default discretizer in Weka, which is a machine learning platform, free platform that's most common in the machine learning world. So just to give you an idea, if you're asked to discretize this, it's pretty obvious that a cut right there is not going to be optimal. Something like that might be okay. You get low entropy over here and fairly high entropy over there. Or another way of putting it is you get homogeneity there and heterogeneity there. Alternatively, you can try that cut, which has a pretty similar sort of look to it. Or you can go for 2 cut points and get very good predictive accuracy out of that. So that's the sort of problem we're looking at. We're interested in moderately complex classification models, so not just a single variable predicting a target, but this sort of bias is certainly desirable. So classification trees with a fair number of branches in them, or Bayesian nets with a fair number of nodes and arcs, and then perhaps 2 or 3 or more attributes that need to be discretized. Okay, so as I said, we evaluate predictive accuracy as a part of this. ROC curves are also fairly popular as an alternative to predictive accuracy. So we looked at area under the curve and our own techniques, which I'm not identifying yet, keeping them a secret for a few slides. Okay, aside from MDL, well actually in addition, MDL in addition gets this, but all the techniques, in fact, had some control for overfitting by the method of cross-validation, which I'll explain in a minute. Combining doing an MML version as an alternative MDL is possible future work. Okay, so before introducing my techniques, I'm going to raise the question, slightly different question, of how we evaluate the classifiers. So there's one question about how do you generate classification, including the discretization. There's another question of somebody having generated such classifiers or a sequence of such classifiers, how do you evaluate either that classifier or the algorithm producing the classifiers? So that's this question. So this is evaluating or measuring the performance of the classifier. Is the question. So we have some classifier. It's a function from some attributes into some classes. The most basic principle, I suppose, is having found a classifier using some training set, then you don't want to evaluate it using that training set all over again. Obviously, because, for example, if you're overfitting the noise in the training data, you don't want to say that, gee, the classifier is doing a really good job because it's fitting noise. We want it to fit the real problem and look through the noise. Since we're often trying to predict class membership, test set predictive accuracy suggests itself. And indeed, that is the most popular way out there presently for evaluating these things. Almost everybody reports predictive accuracy. They do stat-sig tests. They repeat the tests, do stat-sig summaries, and say, oh, gee, I'm better than you. So predictive accuracy in a binomial case, of course, looks like this. We have some proportion of true cases and some proportion of false cases. We have the classifier asserting that a case is true or that it's false. So you have true positives, true negatives, false negatives. The point is that predictive accuracy basically gives equal weight to true positives and true negatives, and equal weight to false positives and false negatives. So there's a simple example. So getting true cases right is just as important, well, as avoiding false assertions of falsehood there, or whatever, 1 minus the error rate. Anyway, the bottom line for my criticism of that is that there are values underlying these cases, correct classification or misclassification, and the values are diverse. They vary from one cell to another. So in particular, deciding that some food, let's say mushrooms, since there's a mushroom database in the UC Irvine collection, deciding that it's edible and making a mistake about that is not of the same value of magnitude as deciding that it's poisonous when it's actually edible. Do we agree? We are so happy. Okay. So failing to eat a good mushroom, it might hurt you all right, but it's not going to hurt you as much as eating a poisonous mushroom. And to be sure, it's also the case that positives here, correct assessments, are not necessarily the same value. Deciding that something that's edible is edible, there's some positive value there, particularly if you're hungry. Deciding that something that's poisonous is poisonous, well, perhaps there's a certain amount of negative value there. You have to keep on hunting for some more food. So predictive accuracy is invariant to the values of the correct and incorrect classifications. It's also invariant to the confidence with which predictions are made. It's basically just deciding that whatever the modal class in your probability distribution might be, that's what the prediction is, and all the weight goes there. So in other words, predicting edibility of a mushroom with 0.51 is treated the same as edibility of a mushroom with 0.99. But once again, that's problematic if you want to live very long. I mean, if you're going to base a decision on that, right, then it's likely you'll come to a different decision in these two cases.
So when you say accuracy, what is your null model relative to which you are measuring the accuracy or scale?
Well, the typical thing would be in the training set, you simply look at the frequency of trues or falses or whatever the classes are, and that would be your prior.
So here, could you use a 50-50 as a null model to?
Well, I think you'd really want to look at the mushroom data set and see how many of these things really are poisonous. Because that gives you some idea of how difficult the learning problem is.
That location is
I'm sorry?
that the location?
Yeah, well, I'm talking about it's really specific to a particular data set. Now, where that data set, I don't know, came from, I don't know. Probably American, but I don't know. They get data sets from all over the place. Who knows? But if you go to the UC Irvine database, they have not just the data, they also have explanations of where the data come from and who you're supposed to acknowledge in a citation when you use it in publication and so on.
But these are posterior probabilities based on some.
Well, I'm talking here about posterior probabilities based on some learning process through the training data. Right. So my point is just that 0.51 for edibility is not the same as 0.99. In particular, if a certain category, suppose B is in some larger class that's still a subclass of the whole. So in math font B or something. If those on average are the prior for B is effectively 50-50 or something, and you get this right, and the prior for this is 50-50, and you get that right. In principle, that should be rewarded more than that, because you're finding something substantial out that isn't there in the prior.
So hopefully, if everything was done well and correct and so on, if there weren't any sort of misconceptions, then the average posterior of the predictions should actually match the fraction of correct predictions when you do a test set. Right? So there should be some connection between those.
No, what's an ideal predictor would take the training data. Suppose 50% are edible, 50 are inedible. The ideal predictor would take that training data and learn so much information from it, so that confronted with a new instance, it would always get it right, edible or not edible.
Well, but then it would
Okay, but
also
then if you
assume
weight that by the frequency of edibility or inedibility in the training data, then of course you'll get the prior back.
That's true, but you should also get the posteriors back, right? So if a guy says, I'm always 75%, if a classifier says, I'm always 75% sure that I got the right answer, then probably you would hope that the frequency of getting it right is also 75%.
Yeah, exactly. That's what calibration means. So here's a typical sort of graph from people who study calibration in cognitive psychology. So if you have some objective probability, well, where do you get that? Well, there are different ways of generating that. For example, I can choose facts out of an encyclopedia and randomly toss a coin to choose which ones I'll invert. So half of them are right, half of them are wrong. So the objective probability there is 50-50. I can do a bias coin to get other points there, and then I can ask people, just to rate the probabilities of the different assertions, and then I clump them into different categories: 30%, 50%, 7%, etc. And this sort of curve is what you almost always get. You get overconfidence. So if the objective probability of something is 0.9, then people are going to tend to tell you that it's 0.99. The real probability is 0.99. So they push up the things that they're predicting are likely to occur, and they're pushed down the things they're predicting are likely not to occur, which of course is the same thing as symmetry. And so the bigger the bend on this, the farther away from the ideal you get, the worse you're doing. So as you were saying, the ideal is on 75%, you predict 75%. It's just that outside of weather forecasters, we don't have very many people who can do that.
So it is actually, there's some similarities with seasonal and climate forecasting in terms of they also look at sharpness and other things to sort of complement.
Yeah, there are lots of factors that enter into this. I mean, there's an underlying tendency that humans have to be overconfident. Everybody has that. But you can dampen it by acquiring more and more understanding of the domain. The more you know, I mean, there's a correlation, an inverse correlation with expertise and miscalibration. Okay, so basically what we want is, I say, is to combine predictive accuracy with calibration, a reward that rewards both of those simultaneously in some kind of trade-off. So ROC curves, predictive accuracy obviously doesn't do that. Predictive accuracy just ignores, as long as you're getting the modal class right, that's it. Doesn't matter how right you are, how confident, or whatever. ROC is the same way. ROC is just looking at predictive accuracy or true positive rate at a particular false positive rate. And then it looks at the whole range, assuming you have some way of tuning false positive rates. Then you can produce curves that are dominant or whatever, etc. But it's all just predictive accuracy. It's completely invariant to calibration. And you can, of course, you can average that by just, so you can say, well, they might not be dominant, right, but maybe this guy's area is actually greater than the other guy, so overall I prefer something like that. Okay, fine. Now here's an alternative. 15 years ago or so, Peter Turney started working on what, from a Bayesian point of view, is actually the optimal idea for doing classification. So this isn't discretization, in fact, this is building classification trees without ignoring discretization. But anyway, the basic point is that you can compute an expected, well, you can compute a utility from actual predictions, assuming that you have a utility function from outcomes to the reals. And what you can do is build a classification tree which maximizes in the training set this kind of function. And that's what he did. And where he was able to get utilities, he demonstrated some improvement over standard information theoretic techniques, for example, which are ignoring utilities. Okay, so it's become moderately popular as a technique for classification learning in machine learning since then. The potential for very substantial improvements in classification was made quite clear. The potential was made effectively by a sensitivity study, so he looked at ranges of possible utility assignments to the outcomes, and given the extremity of ratios in the different categories, he was able to show that in many cases cost-sensitive learning was simply totally outpacing, at least in the extremes, as the ratios got large. Actual improvements are much harder to demonstrate because you need actual utilities, and utilities are a bit hard to come by. I mean, in some cases it's perfectly straightforward, but the UCI machine learning database, in some cases they offer some utilities. For example, the German credit data comes with a utility table. It turns out that utility table is completely useless. It's rubbish. It's a very bad table. It clearly doesn't describe the utilities involved. The German credit data is about going in for a loan, applying for a loan in Germany. I think they're mortgages or something like that. And you're trying to estimate the probability with which the guy will default. And I believe the ratio is 2 to 1. So if you default, then that's 2 times worse than the opportunity cost of not making the loan, which is just ridiculous. The real ratio is more like 20 to 1. So anyway, getting the real utilities is tough. But nevertheless, if you can get them, then that ought to be the Bayesian gold standard for assessing classifiers, and hence also for assessing discretizers, because discretizers are a subclass, if you like, of classifiers. Now this will combine accuracy and calibration. If you increase either accuracy or calibration, holding the other one fixed, that will rise. Okay, so that's for evaluating classifiers, but what I'm suggesting is that we can just take that evaluation function and push it straight into the discretizer, the same way Peter Turner is talking about doing for classification tree building. Instead, we can do it for the discretization builders. So, new discretization method number 1: do optimal search for discretization which maximizes expected classification utility. Of course, this is only going to work when utilities are available. And for this preliminary study, we actually didn't have any utilities, so I can't really demonstrate a superiority exactly. But I can do the same sort of hand-wavy sensitivity analysis that Peter Turner did. Okay, now notice that this is not a scoring rule. This is not a measure of the value of the model directly. For example, it's not a posterior probability of a model given the data or anything like that. So it doesn't have the same feel as MDL or MML. In particular, it doesn't give you any way of controlling the complexity of the discretization. It offers nothing there. But the technique, I'll embed it in a technique which does, so there is some complexity control. Now, the other point is that utilities are often not available. What do we do then? So I have an alternative suggestion here. Looking back at the work of I.J. Good. So I.J. Good introduced a log scoring rule for classifiers, binary classifiers in 1952, that makes a lot of information theoretic sense. It rewards accuracy. It also rewards calibration. It does both simultaneously and in a neat integrated way. It maximally rewards the true probability distribution. So if an oracle tells you what the real probability distribution is and you use it, you get the maximum reward. So in the literature, that's called strict propriety. Again, this is a scoring rule, not a model measure. So here's a simple plot of Good's information reward. So he throws a 1 in here so that it isn't always negative, to make people feel good about their classifications. So suppose, for example, that you classify something as being in class T or whatever, with probability 1, then the log will be 0 and you get a maximum reward, which is 1. Suppose you classify it in the correct class with a probability 0.5, then this corresponds to 1 bit of information, but it's negated. So you subtract 1 from 1 and you get 0. So 0.5 is a 0 point. And suppose you're anti-Bayesian and you assign a probability of 1 to something which turns out to be false, then this turns into negative infinity, and you never recover from that. You go to the Bayesian hell. So that's how his information reward works. And for binary classification, it's fantastic. I mean, if you have something trained up on a bunch of data, you have a bunch of test data, you run through the test data, you apply this information word on each classification in the test data, and you get, I think, almost an ideal kind of score if you're going to, ideal to the extent that you can be if you're ignoring utilities. And you will ignore utilities if you have no idea what the utilities are, right? So, all right, so in 2004, we generalized this to multinomial classes, relativizing the estimate probability of being in class I to the prior probability, the prior and determined the way I said, just looking at the frequency in the training data. And this is what we came up with.
This just maximizes the likelihood, no? Just thinking about this reward is good. Because if you forget about the 1, which is the constant, then it's the sum over the log of the probability assigned to the correct class, which is the, it's like the, it's the same, it's monotonic in the product of the probability.
Okay. But this is doing it in the test data. So you're not maximizing likelihood in the training data, you're not overfitting noise, you're testing. And that's part of the point of this being a scoring rule and not a model measure. Okay, so anyway, here we just have the class that comes up true, all the classes that come up false. So there's a penalty if you, well, there's a reward if you overestimate, so to speak, relative to the prior of what comes up true, and a corresponding penalty there, or a reward here if you underestimate the probability of a false class that comes up false. So you just, generalizing just a little bit, well, just adding over the whole test set and then normalizing so it comes out to be an average information reward per test case. So you can compare across different size test sets and so on, or different areas as well. Okay, so those are the two proposals. One is a cost-based evaluation put into the discretizer. The other is goods information reward generalized and applied. So like I said, in all of that is a scoring rule, so there's no complexity control. We embedded all of these things, including MDL, in a genetic algorithm looking for the optimal discretization according to this criterion or that criterion, so the BIR criterion or the cost-based criterion or the predictive accuracy criterion or the MDL criterion. So the GA does the search for us, and we also set it up so that it does control of complexity for us. We built it as a Weka plugin, and we tested it with these three classifiers, C4.5, naive Bayes, and AOD, which is just an ensemble of semi-naive Bayes models. So we seeded them all with random discretizations to get it started with a small number of cut points, and then use mutation crossover to be able to search the space for the the discretization space. Okay, so what we're optimizing in the genetic algorithm search, not the evaluation, but in the genetic algorithm search itself, was these four things. And this is meant to explain the complexity control. So we used, well, first of all, as in almost all machine learning studies, you start out with a single data set. You don't actually start out with the generating model. Well, you can, sure. But at the UC Irvine collection, you start out with a data set. You typically do 5x2 or 10-fold crossover or something like that. That means you segregate out some of the data to be used to evaluate everything in the end, and then give your learner, your discretizer or whatever, this data. And what we did in the genetic algorithm is we did a further 3-fold cross-validation. So the fitness was computed on some segregated data, while the discretization search or the local search was done on training data. So the fact that you're maybe fitting noise here by having too many cut points would be revealed by a poor performance in the fitness data.
So if that happens, do you then change your test data?
Sorry?
If that happens, what do? You change your test data? Or?
No, if that happens, then this particular discretization is unfit and doesn't get reproduced. So it disappears.
So that means that you have to go and change your model or
Well, we have a population of discretizations out there, 20, 50, whatever. And those that are bad don't reproduce, those that are good do reproduce, and like any genetic algorithm, it's sort of like simulated annealing, you stochastically approach a optimal. Okay, so we have lots of results. This is a very small subset that I'm going to show you, even though the tables are fairly large. But let me just explain how to read the table. The representation that we were running for this particular table in the genetic algorithm was AOD. And the fitness functions, we use all of these fitness functions, and we're comparing these fitness functions against each other, and we're comparing them by way of predictive accuracy. So these are predictive accuracy numbers here. So VIR in the fitness function gave us the best result 3 times in these cases, and MDL, I'm just comparing with MDL actually. So best result means best relative to MDL. Otherwise, these intervals are overlapping. So MDL did best once, and VIR did best 3 times. Here it's the same runs, but they're evaluated with VIR. So VIR fitness evaluated with VIR. That's a kind of bias, right? We use a Bayesian technique to evaluate a Bayesian learner. We expect the Bayesian evaluation technique to reward the Bayesian learning technique. And damn, it doesn't do that. They're all ties. It's very disappointing. I would have expected bias to show through. We evaluate them also by area under the curve, and here VIR is doing even better, so it's got 5 wins against 1. Okay, switching representation, so now it's the same sort of thing, but we have naive Bayes being the model that's being learned in the genetic algorithm. So on predictive accuracy, it's 3-2 VIR. Measured by VIR, there's no difference again. And area under the curve, it's 5-1. And finally, using the classification tree J48, classification tree learner J48, MDL is doing a little better here on predictive accuracy. Again, it's a complete washout in VIR, and it's a washout also with AUC. The overall result, as far as we got in this preliminary study, as I mentioned, is this. Well, summing across all the representations and measured with predictive accuracy, we get a p-value on the binomial sig test. Between these two, we get nothing very interesting p-value. With VIR, again, nothing interesting. But with AUC, we're actually, according to AUC, VIR is actually beating MDL. Actually, in the sense of orthodox statistics, of course. This is another little thing that my student did. Just compared the correlation between VIR scores and AUC scores and got this plot. It's a kind of interesting plot. So what's interesting about it is, well, of course, there's a correlation. You'd expect some correlation. VIR is rewarding both accuracy, which AUC is reporting, and calibration. But you can see that there's some sort of funny thing going on right here. It splits apart. There's a group that has high accuracy, but degrading VIR. Whereas normally the majority, when the VIR degrades, the accuracy also degrades. So that just shows that there's some uncalibrated guys that are doing reasonably well with accuracy. Okay, so this is a cost-based study. It's pretty limited. It's limited, first of all, by the fact that I don't have the data. My student disappeared. I asked him for the data. He wouldn't hand it over. He just disappeared. He left me with these cruddy, obscure graphs, but I'll try to interpret them for you. They do tell some story. It's not completely useless. So first of all, the cost ratio of true negatives and true positives is not indicated here. It's just fixed at 1-to-1. That's, in general, not a very reasonable assumption, but it works well for lots of cases, so we'll just ignore that. Okay, so given that, then this dimension here is the cost ratio of false negative to false positive. So this is BUPA. This is liver damage from drinking too much alcohol. So if you have a cost ratio that's where false negatives are hurting you a lot more than false positives, then the cost-based discretization is clearly doing better than alternatives. And similarly, if you have very high costs associated with false positives, then again the cost-based discretization is doing really well. And the other ones, they overlap a lot, but I guess this is I guess in some sense a simple problem. If you ignore utility and EFB, equal frequency binning is actually doing the best. Australian credit? Yeah? Okay. I'm almost done. Australian credit, this is like the German credit data set, except it's local to me. And in this case, I don't know what you can say. Not much, really. Everybody's doing just as poorly as everyone else. German credit, there's a little bit of an advantage to the cost-based discretization showing up here. and a bigger one showing up down here. So at the extremes, you get cost-based discretization outperforming alternatives, and otherwise it's much of a muchness. Then there are various heart databases from UC Irvine, and nothing much to say there. Not too much to say here either, although cost-based does show some improvement there. And BIR, I guess, is winning a few times as well. Another heart one, nothing much to say, except cost-based discretization is doing fairly poorly in the middle ranges. And diabetes is the Pima Indian diabetes data set, and again, cost-based discretization is clearly outperforming at the extremes. And by the way, the extremes are probably what's right in many of these cases, right? Because the cost of getting a false negative or a false positive on diabetes is real. It's not something one-to-one. Sorry, the ratio is going to be different. That's the real point. Anyway, false negative on diabetes is probably a lot worse than a false positive. You get a certain amount of treatment that you didn't need, big deal. But if you don't get treated with diabetes, you can go blind and all kinds of other nasties can happen to you. Thyroidism, this is a ternary data set. So there's hypo, hyper, and no thyroidism. And in this case, it's kind of interesting. The simple techniques are simply stomped on by BIR, MDL, and cost-based. So, overall on cost-based evaluation, BIR and MDL are pretty similar. Cost-based is occasionally clearly outperforming the alternatives. So it looks like a pretty promising approach. In general, BIR versus MDL, this is very preliminary, very sketchy sort of study, but within the limits of this study, BIR is either drawing or beating MDL on traditional performance measures. So I think that's pretty good, particularly since the complexity control for BIR is pretty ad hoc and rudimentary. The complexity control for MDL, well, that's what MDL is about. It's about controlling complexity while fitting the data. So I presume MDL has some kind of advantage there. So if we look at better controlling complexity, maybe look at different cost validation regimes to do that, for example, then this ought to improve. BIR is a performance measure for looking at these different algorithms. It simply appears to be insufficiently powerful to be useful, which is kind of sad. So, future work, complete the study, especially cost-based, investigate complexity control. Possibly, I might implement and test entropy MML as an alternative to entropy MDL. In many applications, MML has been proven to be superior to MDL, so we might get a win there as well. And then, of course, publish. And once published, we'll donate all the stuff to WEC. It's all written in Java, and it's written to fit into WEC. So that's it.
So we have time for several questions.
So in this case, what would be the difference between MML and MDL?
I answered that yesterday. Go on YouTube and see. No, that's okay. I can repeat. The main difference is just in how it treats parameters. There are other subtle differences and so on. In fact, there's a beautiful set of 3 tech reports written in the mid-90s by Baxter and Oliver and also David Ham on the relation between MML and Bayesianism on the one hand and MDL on the other. So I can recommend those to you. But anyway, in summary form, is in treating parameters, MML treats them as part of the model that actually has to be learned and has an associated complexity with it. So in particular, it uses Fisher information derived from the data to estimate the amount of precision that makes sense to give to a particular parameter. So if you have a lot of data that's not very noisy, you'll get a high precision parameter. If you have little data or very noisy data, you get a low precision parameter. And MDL doesn't go to the trouble. So as a result, MDL is a lot easier to apply. Anybody can apply it. It's straightforward. Whereas MML, if you're applying it to a new problem, you have to solve some fairly complicated mathematics to derive the Fisher information for a new class of model. And so, for example, that's something I don't do. I get other people to do it who are mathematicians. So that's the main difference.
Anyone else? Okay, so let's thank Kevin and